Okay, so generally speaking, we can classify everything as either being matter or energy. And when we're talking about matter, matter can either be a pure substance or a mixture. And when it's a pure substance, you will either have an element alone. So that would mean anything that's on the periodic table. So like carbon alone, potassium alone, okay? Or you will have a compound. Now, a compound is formed when elements chemically combine. So a chemical reaction has to take place, and then we could form something like potassium chloride, or you could form something like, I don't know, calcium phosphide as an example. So you would have more than one element chemically attached to each other, okay? And then if you're going to convert a compound back into an element, this would also be a chemical process that would have to occur in order for that to happen, okay? And when we're sort of like defining what pure substances and mixtures are in terms of properties, pure substances will have the same proportions of components in the sample. So that means there's going to be one set of properties. There would be one melting point, one boiling point, one color, one density, etc. Okay? And then in terms of mixtures, can I move this board up? Okay, so for mixtures, mixtures are going to be where we've got different components that have their own identities. So if I've got two different substances that have different boiling points or different densities and they're mixed together, I can separate them using those individual properties. So this is going to be made of more than one type of substance. And then if I'm looking at an element is something that I cannot decompose into other things. So for instance, potassium is an element on the periodic table. I can't separate that into other elements because it's only made of one type of atom, okay? And then if we're talking about compounds, compounds can be decomposed because if I have something like potassium chloride is KCl. This is made of potassium and chlorine chemically attached through ionic bonds. And so since I can decompose them, that means that they are made of more than one type of atom because I would have potassium atoms and chlorine atoms present. Okay, let's take a look at the next page. Generally speaking, you're going to hear chemists refer to different types of matter like molecules or atoms or ions as a chemical species, or we will just use the word species. Okay, so chemical species are all the different types of particles that we could have in matter. So this could be atoms, molecules, or ions as an example. Okay. And let's talk about elements in a little bit more detail, okay? So down here, they have divided elements into three different categories. So we've got metals, metalloids, and non-metals. The metals are primarily on the left-hand side of the periodic table, and then the non-metals are on the right-hand side. So this would be most of the table are made of metals. The non-metals are on the right of the table, except hydrogen, okay, which you'll see in the upper left-hand corner. And then the metalloids tend to fall along a darkened stair step, which I'll show you in a second. And some of the groups or columns of metals and non-metals have specific names. For instance, metals, we've got the alkali metals, and this would be group number 1. And then the alkaline earth metals would be group number 2, and I'll show you what this looks like in a second, okay? On the right-hand side, the halogens, these would be group number 17, and then the noble gases would be in group 18. Technically, these are the only groups or columns that have official names. None of the rest do, so therefore we just simply use the numbers when referring to them, okay? So let me can I bring this down a little bit? Do you have this? Okay, so on your book, what they've done is they have separated, there we go. They've separated the metals, nonmetals, and metalloids for you. So here you can see that this is in the upper right-hand corner of the periodic table. This is where your nonmetals are. Hydrogen is technically in two different places. It's on the left and the right. I'll explain why that is later on, okay? Then you've got your metalloids here. They're all highlighted in purple, okay? I would know the symbol and I would know the name. Okay, and then I will give you a periodic table. I just have to pull it out and give it to you. The periodic table that I give you has the symbols and the names on it. Okay, and then over here, you've got all the metals to the left of the metalloids. Okay, and this includes the two rows that are detached along the bottom. Now, for hydrogen, hydrogen has properties that are in between metals and nonmetals. And so what they do is they consider hydrogen to be a really unique element. So therefore, hydrogen is considered to be in a group of its own. You will sometimes see hydrogen listed at the top of a periodic table alone, like especially on periodic tables that you download from the internet. Okay? Okay, let me get you you guys are going to want 3 different colored pencils or 3 different colored highlighters, because you're probably going to want to color code the periodic table while you're sitting here, because you'll be using it throughout the class. And then you guys want, let me stop this, you guys want, okay, on the next page, they outline the different properties of metals and nonmetals. I will definitely ask you questions about these on a test. So metals are good conductors of heat and electricity. They are malleable. This is a definition that you definitely want to know. Malleable means that you can pound it into thin sheets. So for instance, we've got aluminum foil that we often use in the kitchen. Aluminum is a metal. Aluminum is malleable. Okay, metals are also ductile. That means we can draw them into thin wires. We often have copper wire in our homes. Okay, and then metals are often lustrous as well. The one misconception that people have about metals is they think that metals are innately hard. That's not true. Okay, like I could actually cut a piece of sodium or lithium with a butter knife. Okay, a lot of things. Alloys, which are mixtures of metals. Alloys are hard. Okay, so everything that I just discussed here, these are all properties of metals. Okay, now a common chemical reaction for a metal oxide, meaning a metal that is chemically attached to oxygen, would be a metal oxide will react with water and it will form a base. Bases contain hydroxide, which is OH -1. Hydroxide is on the bottom left of the periodic table that I just gave you. So when you hear something weird, you don't know what it is probably on the bottom left-hand corner, the name and the formula, okay? Okay, let's go over nonmetals. Nonmetals are terrible conductors of heat and electricity. A lot of them tend to be gases at room temperature. How do I know that? If you take a look at the periodic table on the wall, they are gases because they are red symbols on the table. Okay? If they are solids, they tend to be crystals that are brittle and they shatter extremely easily. How do I know that they are solids? Those black symbols that are on the table indicate that they tend to be solids, okay? And then the blue ones are liquids. Generally speaking, non-metal oxides will react with water, and instead of forming a base like a metal, they will form an acid, okay? So everything that we just discussed here, these would be the properties of non-metals. Okay? Now, there is a trend on the periodic table that you should know, and this is the first trend that we'll be talking about. I'll talk about the rest in another chapter. Moving up and to the right on the periodic table, there is a trend known as metallic character. Metallic character increases as you move away from the nonmetals, so it kind of makes sense. So if you're looking at a periodic table, which looks like this, metallic character would increase in this direction. Make sure you know this trend. Okay, now there are some elements that can group together in different ways or have their atoms arranged in different ways. And these are known as allotropes. Okay, so to give you an example of allotropes, we could talk about oxygen and ozone. So O2 versus O3. O2 would be how oxygen exists in nature. O3 would be ozone. Another example would be the allotropes for carbon. One allotrope for carbon would be diamond, and then another allotrope would be graphite. Okay? All right, let's move on and talk about compounds. I'm going to stop the video here.